Speaker will be Sandra and Mous. So Sandra is a staff scientist at LCLS working in the CXI and MFX beamlines. She supports ultrafast hard X-ray scattering experiments, specializing in time-resolved serial femtosecond X-ray crystallography.
Great, yeah, thank you, and thank you for the opportunity to share some of my thoughts here today. So I'll be presenting a bit more of like a high-level science perspective, because yeah, working as an instrument scientist, I have like a very limited time for like software or data analysis. Also, you may see I'm very active in like time-resolved crystallography. So some of these points have already been presented very well by Nick this morning. So perhaps what my job is here today is to maybe like stress the importance of some of these developments. If it is too much of a repetition, then please just bear with me for 5 minutes. So yeah, what do we do? As presented this morning, we're trying to record molecular movies of biomolecules in action. Something that I've been working on before I came to SLAC is, for example, like charge transport across the membrane. And here we have one of these like membrane proteins where we are looking at like ion transport and how exactly do conformational changes in proteins catalyze these kind of reactions. And this work, for example, we recorded 6 structures at the X-ray free-electron laser, and this is what we call a movie. I guess we can do a bit better there, but good enough, I guess, for now. And what the data set typically looks like is, for example, in this case, since we had low symmetry, we had like 100,000 index diffraction patterns. Now there you need to, of course, like account for like hit rates. Not every single X-ray shot may be productive. And also not every shot can get indexed. So in the end, for this project, you had like an overall indexing rate of 60% being productive. Now, if you then think about the 120 hertz rep rate of LCLS, this means that within 1.5 hours, we should be able to get one structure. And therefore, within in 1 shift or so, we can make an entire molecular. Now, HE, as presented this morning, because we go towards like the tens of kilohertz and ultimately like megahertz repetition rates, will be really like transformative for these kind of experiments, where now instead of like spending 1.5 hours, we can instead start collecting structures within 20 seconds. So here you can see this like time trace that we measured with like spectroscopy, and you see how with these like 6 time points we can really start to hit these like different intermediates, and here we try to really target like the accumulation of a particular spectroscopic intermediate. Now, as you can notice, we still have like quite a mixture, as we have, for example, like a decay of like this K and L intermediate, and then this rise of like the O1 and the O2 intermediates. You can imagine that at the HE rep rates, we can instead like start to like probe the entire time axis and really also start to disentangle some of these like mixtures of intermediates. And now instead of like having like a snapshot collection of frames, we can really start to record like real movies of proteins in action. So yeah, as I mentioned, ideally 1.5 hours per structure at 120 hertz. Now we go to 30 kilohertz in the first years of HE. We have 20 seconds per structure. But actually, the reality looks a tiny bit different. As you may know, some of these experiments take actually like several shifts, so several, let's say like around 60 hours rather than 10. And I would say that for this experiment that I've just shown, we needed like 6 hours per structure at 120 hertz rate. One of the inefficiencies that we encounter is, for example, delays because of like beamline alignments. So think about the pointing of the X-ray beam, continuous monitoring, but also like the focusing. So really getting like the best X-ray focus at the interaction point. In case of like optical pump probe, we have like laser tuning. So think about like really like tweaking the compressor, for example, like measuring the power, looking at the alignment, spatial overlap, swapping out samples. And also something that was discussed today is like really like this like data analysis and decision making. Whenever we encounter a lag there, you can imagine that we really like over collect while we like decide whether we're ready to move on to the next time point. So therefore, in our current state, like just like increasing the repetition rate of the X-ray sources is not necessarily going to shorten data collection times in a linear fashion. So what if we now introduce like, high performance computing? So we want to look at like this structure and dynamics. And as I mentioned, instead of like just probing like T1, T2, and T3, like measure the entire time scale. But in addition, we collect a lot of like information that we can use for further like improving the efficiency of these type of experiments. So for example, you can think about like experimental steering. So now instead of like having the human in the loop, try to automate things as much as possible, such that you have data analysis and statistics deciding on when it's time to swap samples, when it's time to, for example, like choose a different like time delay, or also, for example, like automatic alignment of like beamline components. Other opportunities are, for example, at the merging step as well. So really looking at like data, like statistics, and whether you, for example, like reach completeness, and whether you're ready to move on to the next time point. And ideally, you might also think about, for example, like automatically like driving and like probing this like energy landscape. So really removing the human process. Of course, also, all of you are aware of, like, for example, like models like AlphaFold as well, and like in silico procedures these days. You can think about coupling these type of experiments to, for example, like a dynamic type of approach to in silico modeling. And of course, there's a lot of like exciting applications in coupling like molecular dynamics simulations with these kind of like time resolved experiments, and perhaps even like further refining like force fields for these kind of simulations. Further opportunities exist when it comes to like high repetition rate X-ray free-electron lasers into like really going from like a reaction coordinate towards like these like energy landscapes. So classically, most of our current experiments at LCLS1, we make use of, for example, like optical pump probe, and really look at like time-resolved experiments. So now we trigger the reaction and then follow in time the reaction coordinates as it progresses. As Nick has shown this morning as well, this can be, for example, like an optical pump. It can also be like mixing, and so on and so on. However, there's many other parameters that are very exciting and interesting to investigate, such as, for example, laser parameters. Think about the laser power density as shown in this publication here from last year, where you can find like different structural intermediates as a function of like the laser power. You can also think about pH and protonation states, that is here shown, like where if you change the pH, you actually start sampling different conformations, which can have like different catalytic efficiency. Another one is, of course, like temperature, very exciting area as well, that is like really up and coming and becoming more popular, as well as like hydration. If you change like the moisture and water content, humidity, you can also see like structural changes, or even like changes, pretty drastic changes in unit cells. And then also, of course, this like latest beautiful work from the Hexer group on, for example, like applying electric fields. So really simulating the environment that transporters might see when they're like located in the cell. So with that, I think the future of crystallography at LCLS, we are going towards high throughput. We're also going towards like multiple states. And then finally, also like multiple conditions, which is like endless opportunities and like combinations as we move from like a linear scale towards like this really like multidimensional energy landscapes. And therefore, we need more computing, more bandwidth, more storage space, but also like more monitoring and better capturing of all this like metadata to like find out where we are in this dimensional space.